Good afternoon, everyone. My name is Terry McVenis, the President and CEO of RTCA. Greetings from our nation's capital, and welcome to all of you to our third in a series of webinars, Aviation Technology Connect. Now, traditionally, RTCA has always produced an annual Global Aviation Symposium during the month of June. However, given the situation we're in with the COVID-19 pandemic, we've created this alternate means via this platform where we can hear from a variety of aviation leaders on a broad spectrum of topics that will educate you, further inspire you in your profession, and perhaps even evolve your thinking as to where the industry is today and where it's going in the future. I want to give a special shout out to our international audience that we have with us today. Online are 134 representatives from countries outside of the United States, including Canada, several countries in Europe, the Middle East, Africa, South America, Australia, and New Zealand. Your participation across multiple time zones is very much appreciated. Now, our first two webinars in June and this past July were very successful. In June, we heard from Mr. Wayne Monteith, the FAA's Associate Administrator for Commercial Space Transportation. And last month, we heard from the Honorable Robert Sumwalt, Chairman of the National Transportation Safety Board. Our audience also heard from industry leaders such as Mr. Greg Leone from the MITRE Corporation and Mr. Pete Bunce from the General Aviation Manufacturers Association. And we believe that today's webinar will be equally exciting and informative. Now, these previous webinars were recorded, as is this one, and you can find those recordings on RTCA's YouTube channel. So today and throughout the balance of the year and into next year, we're going to be convening on this third Wednesday of each month at the same time, and we'll continue with this program series. And each webinar is going to first focus on a primary topic, and then we'll include a short tech talk from one of our industry leaders that will share some of their insights with you that I know will be inspirational, strategic, or thought-provoking, with the primary goal of giving you, the audience, the gift of their knowledge. And we're also going to be using this webinar series to acknowledge several of our special committee members from government and industry that have done some outstanding work in the development of aviation performance standards throughout this past year. Now, I'm most grateful to our sponsors from the industry that have come forward to help us make this series happen throughout this year and into next. Without their assistance, this webinar series would not be possible. And for today's event, I'm pleased to have Collins Aerospace, the National Business Aviation Association, NBAA, American Airlines, the Aircraft Owners and Pilots Association, and Garmin as sponsors for today's webinar. On the handout tab of this platform, you can find some additional information that some of our sponsors are supplying to you. So let's get started. Now, access to aviation radio frequency spectrum is something that is vital to everything our industry designs and operates. Traditional aviation operators, as well as the many new entrants to aviation, depend on that access to ensure safety for passengers, cargo, and crew members. However, new technologies are coming to the market, like 5G, for example, that have the potential to impact the current systems that are using the same or adjacent frequency bands. Today, we have a panel of experts on this topic to discuss this issue and how access to frequency spectrum is not only vital to the industry, but how it's driving changes to the industry as well. So leading the panel discussion today, I'm pleased to introduce Mr. Andrew Roy, who's the Director of Engineering Services at Aviation Spectrum Resources Incorporated, ASRI. ASRI acts as the focal point for U.S. airlines and other commercial aviation operators on spectrum engineering and regulatory considerations. He is Vice Chairman of ICAO's Frequency Spectrum Management Panel and is a member of the U.S. Department of Commerce's Spectrum Management Advisory Committee. Mr. Roy is a veteran of the UK Royal Air Force with a background in RF battlespace management. He earned his master's in systems engineering from Loughborough University and is a chartered engineer at the UK Institute of Engineering and Technology. Andy, the floor is yours.
Thank you, Terry, and good afternoon to everyone joining us, or even, as Terry mentioned, from the international audience, good morning, good day, and so forth. Glad we could convene this and have a wide attendance to talk about what, for many people, including myself, is certainly a niche subject. As a comms engineer, Spectrum didn't really come into it until I started my career in the Royal Air Force and got a posting. which dealt with spectrum. And it was unknown to me at the time about what it actually meant and what it would become to be that as well as we went through. So really excited today to talk with a selection of panelists, which we'll get to shortly, representing both from the regulatory side through to the manufacturers and then the end users as well, about what spectrum means and what it can do or cannot do for us as well sometimes. Because as I mentioned, this is a rather niche subject, what I wanted to do was set the scene with a few slides for a few minutes at the start about what spectrum is. And for those of you unfamiliar with spectrum, the best way to think about it is basically as radio frequency infrastructure. It is the infrastructure that allows a wireless application to transmit. From a spectrum perspective, it's a collection of frequencies that are reserved or allocated, as the technical term is, to each wireless function to function. If you don't have that wireless allocation, you can't transmit. And therefore, it's very essential for us as an aviation industry, where we need to have spectrum, given we have mobile air platforms, to operate. Wires don't tend to work very well for aircraft, unless you're a kite, obviously, but that's a fairly niche area. But we need to have that infrastructure in place to be able to do all the comms, navigation, surveillance functions that we have. And if something happens that limits or takes away that function, then we have problems. We're also fortunate in aviation to have what is called safety spectrum. So this is internationally recognized as a safety allocation, as it's called, that puts certain requirements on national regulators to protect that spectrum from interference and ensure it operates in accordance with international requirements to achieve the safety purposes that we use it for. Now, management of spectrum is a very unusual problem for a lot of industries, partly because every industry needs to have wireless access for the various applications they have and the different technologies that go into it as well. And often the analogy is used is basically like a real estate analogy, where you're trying to pair like with like to operate appropriately. A great example of this, and an allocation people probably know, unwittingly at least, is FM broadcast, 88 to 108 megahertz. That 20 megahertz of spectrum is allocated to FM broadcast. But from a spectrum management perspective, at that 108 megahertz boundary, above that, we enter into aviation's VOR, ILS, GBAS, and even further up our ATC voice and data frequencies. So to achieve that spectrum management, actually restrictions were placed on the FM broadcasters below 108 megahertz to avoid as much interference as possible. But also aviation needed to adapt some of its systems as well above 108 megahertz to ensure it was immune from those high-powered broadcast systems. Now, what I want to show here on this next slide is a bit of an eye chart, and I apologize, it's not intended for people to read, but just to give an example, coming back to that real estate analogy. This is a large chunk of the spectrum in use in the US at the moment from the national regulator. And those different color codings are basically different zoning for spectrum applications as we go through. And you've got the high frequency at the top there, very high frequency, ultra high frequency, and then super high frequency down at the bottom there. And as you can see, everything's organized in a certain manner. To give an idea of how aviation uses this, though, to sort of simplify it slightly, if we skip through very quickly, you'll see these are our communication frequency bands. These are the systems we use for our primary comm systems, from HF oceanic comms at the top there, all the way down to the new Aeromax system in the 5 gigs down at the bottom there for the lower green. We then add our navigational systems on top of that as well, from ILS down to radio altimeters and other systems. And then also our surveillance functions added onto that as well. So long range and terminal Doppler radars and so forth, all added in. And as aviation doesn't operate in isolation, we also use several other systems and spectrum allocations to operate, such as ground radios for airport operations, or even SATCOM to the aircraft for Wi-Fi for passengers. So as you can see there, from that chart, which looked fairly large, actually aviation is using a lot of spectrum for all the different functions it needs to operate. And if you took any one of those away, that would cause issues. Imagine not having VHF voice or radio altimeter operations or oceanic HF. Suddenly that becomes a very large concern, and hence why aviation spectrum is very important to the industry. In terms of defining the spectrum environment, very quickly, so everyone wants to be wireless these days. All industries want to be wireless, and if you can sell it in HD, then even better. So there's a lot of demand for spectrum to come in for these wireless applications to be there. A good one that everyone has probably heard of is 5G, very prominent at the moment in the news, and a lot of push to get 5G implemented internationally, as well as obviously in the US. With all that push and demand becomes certainly a high price that's attached to spectrum at the moment as well. One estimate for a current auction that's being looked at the end of this year in the US for 5G would, for one auction, release between $30 and $50 billion for the US government. And US regulators and other regulators love this, because essentially you are effectively selling free air for a 10-year rental, and after 10 years you get to sell it again as well. So it's very popular to sell spectrum or repurpose spectrum, given the amount of money that's involved, especially for these new wireless applications. What complicates this entire process a little bit is that from the chart, although you wouldn't be able to see it previously, there are no unused frequencies left. There's no TBCs or this is left for the next 20 years because we expect something to come in. All spectrum is currently used at the moment. So if you have a new wireless application and therefore you need new, as it says there, spectrum, it's not actually new. You're either going to be repurposing it from another industry who either is no longer using it, or sometimes you can convince a regulator that your priority is higher than theirs, or you need to find a way of sharing with those existing industries to make sure it works. And as a result of this, a lot of industries are in competition with each other to ensure they can either protect their existing spectrum or promote new applications to ensure they can continue to expand and grow, as all industries try, obviously. So what I want to do now is turn to our panel, who I'm very happy can join us today. First, on the regulatory side from the FAA, I'd like to introduce Mr. Michael Richmond, who is the manager of the Spectrum International and Planning Team at the Spectrum Engineering Services Group at the FAA. He has worked at the FAA Spectrum Office for his time as the FAA for the last 20 years, and 2 of those have been as the manager. Mr. Richmond serves as the FAA's primary representative to the Interdepartment Radio Advisory Committee that advises the National Telecommunications and Information Administration, NTIA, on telecommunication matters of the executive branch. Prior to working at the FAA, Mr. Richmond worked at NTIA for nearly 10 years. He started his career back at the FCC, and over Mr. Richmond's career, he's worked to protect aviation spectrum domestically and internationally. He's worked with other agency representatives, international delegates, and industry on many challenging topics that face the aviation community. Mr. Richmond believes the aviation safety and regularity of flight is not only an agency mission, but one that can support in good conscience as well. Mike, thank you for joining us today. Really appreciate you having me on the panel. Next, I'd like to introduce Dr. Sai Kalyanaraman from Collins Aerospace. Dr. Kalyanaraman is a technical fellow at Collins Aerospace, where he supports GNSS, receiver design, and development alongside a range of spectrum activities and industry standardization efforts. Sai also chairs the GPS Interference and Antennas Working Group within RTCA Special Committee 159, and he also co-chairs the Operations Committee within the NDIA Spectrum Working Group. He also represents Collins at a variety of fora, including EUROCAE and ICAO, and his areas of interest and expertise encompass spectrum strategy, adaptive signal processing, GNSS receiver design, antennas and frequency references, and nav sensor integration. And last but not least, I'd like to introduce Captain David Zambrano from United Airlines. Captain Zambrano brings 30 years experience in the aviation industry to his current position as Chief Technical Pilot Communications for United Airlines, responsible for the technical communication strategy and future equipage. His experience in training, operational management, and technical pilot skills helps bring a new perspective to the future of communications. He is rated for the 737, 757, 767, 747, 400, and the A320, and he also currently flies 757 and 767. Mike, Sai, and Dave, I do appreciate you coming on today. Thank you so much for your time. What I'd like to do is kick off and just each of you, just as a starting opener, if I may, ask you, what does aviation spectrum mean to your organization and industry? Mike, if I could start with you, please.
Sure. Good afternoon, Andy. Good afternoon, everyone. Can everyone hear me okay?
You're good, Mike.
Very great. Thank you for inviting me to take part in this distinguished panel. It's a great opportunity to share thoughts on topics that are important to aviation. To answer your question in a word, everything. Aviation spectrum means everything to the FAA. The FAA operates a variety of communications, navigation, and surveillance systems that operate in spectrum from the hundreds of kilohertz to the tens of gigahertz. In terms of frequency assignments, which are equivalent to FCC licenses, the FAA has the second most number of assignments in the federal government. That's a large footprint. Our Spectrum office touches every FAA program management office that has transmitters and receivers. We also work with the Office of Commercial Space Transportation and the UAS office. Our office coordinates with other agencies for activities such as fighting forest fires and for hurricane recovery. We coordinate air shows. We also coordinate with the military for their exercises, just to name a few things. The National Airspace System would not exist if it were not for aviation spectrum. And for the most part, that spectrum is free of harmful interference. When harmful interference does occur, our office quickly responds to eliminate it. Our office often works with our regulators, the FCC and NTIA. We also work with industry groups, companies, standards bodies, and international organizations to plan, manage, and protect the spectrum for aviation. Some of the entities we encounter have other objectives that have the potential to adversely impact the use of the spectrum. It is a constant challenge to keep pace with the new threats and keep spectrum available and interference-free. Our work with ASRI and RTCA are a big part of the aviation community's success. Thank you.
Thank you, Mike. And Si, if I can ask the same question of you as an opener, what does aviation spectrum mean to your organization?
Yeah, thanks, Randy. Thanks for the question. And thank you, Mike, Dave, and the team over here for being part in this panel. I appreciate being a part of this panel. Appreciate the opportunity. From the perspective of a company such as Collins Aerospace, which is part of Radio Technologies as we speak today, in one word, if we were to characterize what spectrum means, I would say the lifeblood. That's just talking about aerospace, but across the board for Radio Technologies and the industry as a whole. From Collins' perspective, spectrum characterization and utilization is part of the fulcrum around which our products are built. As you've probably seen in the handout and the fact sheet that's been provided, we have a variety of products that span the gamut of civil certified and military avionics solutions. When it comes to the civil certified avionics solutions, and to a good extent within the military avionics solutions as well, we are dependent on relevant regulation, global harmonization, appropriate guidelines on what it takes to be able to utilize the spectrum and design products around utilizing the relevant spectrum. So I can give you some examples in terms of communication, navigation, or surveillance products. Whether you look at VHF products or you look at navigation, the DF products. Can you guys hear me?
Yes, we can.
I'm sorry, I thought of that. Thank you. So when you look at communication or navigation or surveillance products, you look at a simple product like a VHF phone system, or you look at a nav product like a DME system, and or a surveillance product like ADSP. You're looking at utilization of spectrum in the lower frequencies all the way up till the mid L band. And for us to be able to utilize the spectrum to build our products, we need to have specific guidelines and specific requirements on what that spectral utilization has to be. That encompasses all aspects of aviation, whether it's a receive system or a transmit system, what the adjacent band compatibility needs to be, what's the in-band compatibility. So there's a variety of aspects that are built around the spectral utilization, and we need to be compliant to that so that we're able to harmonize it globally and we're able to provide our customers and all the relevant aviation stakeholders, and this includes every single person who's flying, an uninterrupted, seamless, continuous service that expect. In the aviation world, when we look at spectrum, as Andy referred to earlier, we have protected spectrum as well, and we have specific requirements around the operational continuity that we have to provide at a product level. And again, that references back to what level of guarantees we can get on said spectrum. There's been several stakeholders from a spectrum perspective who may be not aviation stakeholders who have discussed aspects of spectral utilization and things like harm crane threshold and 99% thresholds. But from an aviation perspective, 99% typically doesn't necessarily cut it. We are looking at 5 nines or 7 nines very often when it comes to continuity of service. So we're looking at something that's 1E minus 5 or 1E minus 7 in terms of continuity of service. And our expectation is when you look at the worst case from a spectrum perspective, we are able to access that spectrum in support of continuity of service. So from a military side, when we're looking at it, the perspective of whether it's the application for EW or element, there are certain expectations that we have on said spectrum, and we need to ensure that those expectations are in line with the global harmonization of that spectrum as well. So with that, I'll pause and turn it over to Andy.
Thank you, sir. I appreciate that. And Dave, from the operator's perspective, again, what does aviation spectrum mean to United in this case?
Well, thank you, Andy, for the introduction, and thank you, Terry and RTCA, for providing the opportunity to talk to you about spectrum and how it relates to really not only United, but the aviation industry as a whole. Aviation spectrum plays a vital role in the service that the airlines provide. And I would venture to say that without it, we would not be able to fly in the current environment. And so when we look at operationally from how we use spectrum provides the means to communicate, and to communicate information that's divided. The way I look at it is into two areas. One is strategic, and then the other one is tactical. Strategic is the plan that you devise based on the information you have at the time, and the tactical is the real-time result of that plan. Both of these use the majority of the spectrum, and we also use voice and data to do that. Based on the audience, there may be a lot of people that may delve into aviation and a lot of people that are relatively new, but I figure the easiest way to really understand that, to make the point, let's take a look at a typical flight from a spectrum perspective. If you go into flight planning and we look at the strategic side, as you start flight planning, one of the things that we start initially doing is we gather the weather information and start looking at the plan on where we're going to go from point A to point B. Well, that weather information is gathered from satellites, and now the satellites have the protected spectrum that we use in relative to that. We also gather our performance data through the internet and intranet using a variety of means, including Wi-Fi. Again, we talked about that protected spectrum. In the planning stages, we're looking at passenger data, cargo loading information. At our airports, we use the wireless networks. And we also, scan our bags. Every bag that goes on our airplane is scanned. We're using that different form of wireless at the airport as well. From a pilot's perspective, we've transitioned from paper into using a electronic flight bag device. For us, we use our iPads. Those devices are using the cell networks and Wi-Fi networks. So for flight planning, once we're at the airplane, flight attendants use onboard devices for customer service and communicating information that way as well. And those are connected to the cell networks. Our maintenance techs are working around the airplane. Our maintenance techs use our iPads, again, via Wi-Fi and cell for the quick delivery of real-time information. And our maintenance techs are an incredible part of our team as well. When you start looking around the airport, VHF, or the VHF radio frequencies, from not only customer service standpoint, communicating with our operation centers, but also on the ramp. And then when we're ready and sitting in the cockpit, we also use VHF communications to our own operation centers. We use the cell networks as well to deliver text messages to passengers for real-time status of the flights. And then we also use what we call our aircraft communication addressing and reporting system, or as we call it, ACARS, for real performance information and communication to our ops centers. We've, for the most part, moved into a paperless environment, and ACARS is a critical infrastructure to our operation. And that is using both the VDL Mode 2 radio on the data side and other networks. We also then, prior to flight, when we gather all that information and we're ready to push back, we need a clearance from air traffic control. So we're using the current system, the controller pilot data link communications, or as we call it, CPDLC, to communicate with ATC and gather our clearance before pushback. And that's going over the VDL Mode 2 radios. And if in fact that some airports don't have that, then we'll communicate via our VHF network. If we're having an international flight, we'll check our SAT voice and ensure that the SAT voice checks prior to departure are working. We do our high frequency checks as well for international and Class 2 navigation. So you can see there's a fairly wide variety, and we haven't even taken off yet. We're still in the strategic phase. GPS is also a critical infrastructure to our operation. It ties in with our flight management computers, and it gives us the location. And so that location has to be constantly be updated and is a critical part, again, to the infrastructure. All that is prior to flight. Once we push back, we now enter the tactical phase, if you will, and we see if our planning actually worked out. And so now we enter in and we communicate with air traffic control on the ground via the VHF frequencies. Once we move on and are departed or have departed, we start communication now and domestically using CPDLC to communicate, which cuts down on the voice traffic. It offloads the congestion issues that we've had previously. And what's interesting when we start talking about spectrum is to look at it pre-COVID and then current COVID, and then look to the future. So in the past, we had quite a bit of congestion. Right now, as the flights during this COVID environment have been reduced considerably, that congestion's been eliminated. But when the number of flights comes back, we'll be back to exactly where we were, I would say February of 2020. As we're flying, if you continue on and we're continuing on to fly, we use our weather radar for tactical offsets and reroutes around current weather. Well, that weather radar has its own particular spectrum. You talk about equipment on board the airplane, radio altimeters. We use radio altimeters that are tied into multiple things on our airplane. Those are also using spectrum. While we're in the air, we get real-time updates, and we're able to use our electronic flight bags for information that's coming off some of the Wi-Fi network. As a passenger, and I know we're all passengers on board their airplanes, me included, but as a passenger, I want my Wi-Fi to work, right? So passengers have the Wi-Fi, and we're using the satellite broadband to provide that piece of information to them as well. En route data downloads for engine and airframe performance are a huge piece right now, and a huge increase in the data that's coming across right now and taking a fairly large part of the ACAR's data traffic on the VDMO2 radios. Our nav aids, each one of those particular nav aids, you can talk about it either from the VORs or variable omni range receivers to the ILSs, instrument landing systems, to the GPS systems, and GPS looking at GBAS approaches or ground-based augmentation system approaches. All of those need to have and utilize spectrum. So from beginning to end, strategic to the tactical, spectrum is integral to the safety of the flight. When you start looking down the road, and as both Mike and Cy have talked about, when we talk about that spectrum, two things come to mind. We have to have a set of standards that we need to follow because it's fairly significant. And the standards provide an expectation to the users, that being us, who purchase a lot of that equipment and use that spectrum along with ATC. So standards are incredibly significant. And then beyond that, looking to the future, when we start looking at that, any new entrants into aviation or any new types of technologies that may come around, really need to take a look to ensure that those technologies do not interfere with a lot of the equipment that we have currently right now. And as we look to the future, I think one of the things we need to do is to start looking at updating a lot of the standards related to each piece of equipment that we have on board. And so that we as the end user want to be able to take advantage of a lot of those types of technologies, 5G being one of them, internet protocol, if you will, being another one. And we need to explore ways to get a lot of this data and communication onto and off of the airplane. One perfect example is who thought we'd be using cell networks on the ground for providing data transmission, and yet we're using electronic flight bags with cell networks that provide that. You look at some of the other technologies with offloading data when the airplane arrives on the ground that are being developed, WiMAX being one of them, Airbus and Boeing both in development of that. Are there different ways we can offload the data so that we can still enhance and protect the current spectrum that we have, but take advantage of the future technologies? And I think that's something that we all need to be kind of taking a look at and working as an industry moving forward. Thank you.
Thank you, Dave. And as you mentioned there, I mean, that strategic and tactical is a great way of framing it in terms of all the systems we do. Maybe focusing on that, and perhaps a question for Cy here on sort of the design and some of the systems as well. Do you think the aviation industry has enough spectrum to support its media functions, which Dave highlighted there? And is aviation industry doing enough with what we have at the moment?
Thank you, Andy, for the question. The answer for that is multifaceted, and let me start with one aspect of it. As was shared earlier on the screen, aviation does have a fair cut of spectrum here in the US and worldwide. But that being said, as things stand right now, aviation is utilizing its spectrum in support of its near-term and midterm needs. Looking forward with all the newer services that are coming online, aviation is at a particular point, I would say more so crossroads in terms of figuring out how to go about supporting all those new services in the existing spectrum. So when you look at the lower frequencies and all the way up to 30 gigahertz, in line with some of the charts that I shared, there's a fair cut of spectrum that aviation utilizes. However, when you look at things like enhanced vision systems, you are looking at spectrum that's north of 30 gigahertz possibly. And for example, there was a Part 87 update where a company like Sierra Nevada Corporation asked for access to 94 gigahertz in support of their navigation spectrum utilization applications. So in short, aviation industry has a fair swath of spectrum to utilize today for its immediate functions. However, there is additional spectrum that aviation is going to need, very much like some of the other users and stakeholders such as telecom, as we expand capabilities and services in support of the operations that we need to do. That being said, are we doing enough with what we have? That is the other facet of your question. We are fairly optimal today vis-a-vis the requirements that need to be met and the existing spectral neighborhood that we need to work with. And as we go forward in this discussion, there are certain elements that we will discuss in terms of new entrants to spectrum and spectrum repurposing. However, that being said, for the spectrum that was characterized at the point where the systems were designed and certified, the utilization is quite optimal. However, the utilization of spectrum as things stand right now and as we move forward is evolving. It's fairly fluid. There are newer entrants, there are newer utilizations and applications for spectrum as we move forward. And the question turns to, are we optimal in view of the future utilization of spectrum, be it for aviation or other adjacent band systems, or other systems that are co-located in frequency perhaps as well. And from that perspective, there is a charter across industry for us to be able to innovate our utilization of spectrum. And we have to be able to do more with the spectrum that we have. Another item I'd like to share with the group over here is when you look at aviation spectrum, and an excellent example is the 960 to 1215 megahertz band. I keep coming back to that frequency slice primarily because pretty much every system in that band today is a pulse system. You look at DME systems, you look at ADSB systems, you look at TACA and JTIBs, and if you set aside the GNSS L5 system, which is a system where the signal is pretty much part of the noise, and you throw a spectrum analyzer scope at it, you go across 960 to 1215, you're not going to necessarily see a continuous peak above the noise floors there. Well, there's a reason that spectrum has been set up that way. It's looking to be compatible with all the other aviation sources in that spectrum, and there has been extensive analyses that industry and regulators have performed to establish compatibility with that spectrum. Now, we have a newer entrant in that spectrum, such as LDAX, that is looking to provide a CW signal, although at a lower power level, and we are in the process of evaluating compatibility. So that is part of, are we doing enough with that? So when you look at a system like LDAX, and you look at the compatibility needs with a system like LDAX, we have to go ahead and innovate. We have to establish what it means to be able to be compatible with a system like LDAX and design, develop equipment, and field that equipment to be compatible with the existing uses of aviation spectrum. So, case in point, if I have to put LDAX equipment onto an aircraft, I need to ensure that I have the right antenna apertures, I have the right level of isolation with other co-located systems, and I have the
Correct.
right level of compatibility with systems on other aircraft as well. So that is part of the innovation that needs to go in place, and we need to address that as we move forward. And that essentially is one example of the framework that we need to have in place. And we are discussing these in different aviation fora as we speak in order to support future utilization of the spectrum that we are essentially tasked with as we move forward from the perspective of protecting aviation safety requirements. I'll pause there and turn it over to any thoughts or questions that you and the team may have.
Thanks, Si. Dave, did you have a point on that?
Sure, and I agree with everything that that Si has said, and I've been working with Si on with the SC239 with RTCA. If you look at pre-COVID, when we were up until, I would say, again, back to February of 2020, when we had a growth rate on average of about 2% per year in the ATCs, as far as traffic, we were using the VDL Mode 2 radios, and that was to offload the congestion that happens as a pilot when you're just trying to get a word in edgewise as we arrive into fairly congested airspace into a lot of the major hubs around the country. The Northeast corridor being one of them in the New York area, and most commercial pilots know that as you're coming in on a typical day when everything is going well, there's significant congestion of flights going in there. And so trying to get a word in edgewise, if you will, with your clearance and provide the timely information back on the voice network was relatively difficult. Thanks to the development of NextGen and working with domestic CPDLC, which is a way to offload the voice communications onto a data communications directly with air traffic control, that has helped significantly and to reduce the congestion in those particular areas where CPDLC is currently active. Right now, there are 3 major centers that are operating with it. The rollout, once that rollout takes place, that's going to provide a fairly significant offload of the voice traffic, which will provide more time to allow for the voice to continue, if you will. But even when you're looking at the CPDLC environment and the VDL Mode 2 radios, if you look at Europe and what they're doing there as well, you get a congestion somewhere around a 40% usage rate when you're dealing with VDL Mode 2. So around 40% on the usage rate, you start getting collisions on the message sets that go across. And so now you actually have to offload and look at other areas or increase the frequencies for the VDL Mode 2 as well. So with that in mind, that was pre-COVID. Currently, with the way the traffic is expected to return, personally, I wish that traffic would return ASAP. But you're talking about 18 months to down the road, give or take somewhere in there. I hope sooner. But there's a little bit of a time frame that we have to work with, and then we'll be back to where those particular levels were back in February of 2020. That being said, if you look forward, where will we be in 5 years with congested airspace and the data flows, and it's the data rates and the offload that we have. And so from a futuristic standpoint, like Si is saying, I think the time is now that we need to be looking forward to the future, because to implement any type of technology, it takes a fairly considerable amount of time to get those regulations and standards worked on and changed. And so I congratulate the FAA in working here recently to move things relatively forward as it relates to different regulations. I would ask that they move at a faster pace, but always with safety in mind, as we look forward to new technologies that are coming around. And then with those new technologies, we have to protect that spectrum from a safety standpoint, as Si has said, so that anything we put on board that airplane, what area of spectrum or what other type of equipment may it interfere with, and how do we protect that? And so my thoughts. Back to you.
Thank you, Dave. If I can move on, and obviously spectrum is a key topic for many proceedings in the US and other countries as well for different things like aviation systems. Do the recent aviation concerns with decisions by the US's FCC affecting GPS, SATCOM, and radio altimeters provide any feedback on how aviation should address spectrum issues, and how should these improvements, if there are any, be implemented? Mike, if I could come to you first from the regulator perspective.
Sure. Well, for the FAA, the regulators are actually NTIA and FCC, and any changes that they make have a drastic effect on how the FAA manages spectrum. The FAA has to be vigilant to ensure that NTIA and FCC ensure that the FAA position is considered with our goal to keep safety in mind. Changes in regulations can be positive or negative. You may remember the new 5 gigahertz allocation that was made to the Aeronautical Mobile Route Service allowed the introduction of Aeromax. But more recently, a new allocation of the mobile service in a band near adjacent to the band used for the altimeters does have the potential to cause interference to some altimeters. So when regulators consider new allocations, the first question should be, what would be the impact to incumbent systems that are co-channel or adjacent channel? That is compatibility. What is the compatibility with incumbent systems? Is it feasible? Trying to make a decision to develop a new allocation is always questionable if you don't consider the compatibility question first. Thank you.
Thanks, Mike. Any other comments? I know, obviously, as Dave mentioned, Dave and Si have been involved in RTCA 239, which is the radio altimeter issue. Any thoughts from yourselves?
Yeah, this is Si here. One of the things that we need to be cognizant of as we move forward is the ability to provide clear guidelines to non-aviation stakeholders on what the competitive requirements are vis-a-vis the specific aviation system that we're looking to protect. So going back to the activities that took place within SC 159, for example, for GPS, for aviation, there was an out-of-band interference mask, and there were relatively clear guidelines on what the competitive requirements are vis-a-vis that out-of-band interference mask for a system that could be located right next to GPS and frequency. So we were able to perform analyses with those ground rules, and there was clear understanding on both the aviation side and the other spectrum stakeholder side and the telecom side in order to ensure that we come up with the right framework to be able to perform those analyses. Now, that wasn't necessarily available when we did the analyses for the radars. The radar systems were developed, 35, 40 years back. The MOPs are at least 38 to 40 years old, if I do the math right, when it comes to the ED MOPs, which is the European version of the radar MOPs. And the spectral environment under which these systems were developed were fundamentally different. In fact, that environment still holds today. And to Mike's point, when you put forth a high-powered system in a band that used to have a low power spectral flux density, you'll have to look at the compatibility with other systems that are making assumptions on what other bands. I'm sorry, I think there's some noise on the line. Can you guys hear me?
We can, sir.
Okay. And so there's an expectation on what the compatibility with other systems in the said aviation band would have to be. So, for example, if you look at the activities that are saying today in the 3.7, 3.98 gigahertz, that band is 220 megahertz away from the lower end of the radar spectrum. However, the power levels that you have in that band and the expected spurious emissions that are currently proposed vis-a-vis FCC regulations in that band need to be looked at closely, which is what SC 239 is doing right now in the context of protecting the existing certified radio altimeters. And this brings us to another aspect of spectrum compatibility and how aviation is going to be able to be compatible as we go forward with other utilization from a different industry standpoint, say telecom or other SATCOM systems. This goes back to the rate at which things evolve, the rate at which things are fielded, and the rate at which these things are rescinded from the system. So when you look at aviation systems, for example, if you go to radar altimeter, there's an expectation these things would be in service for about 25 years. It takes anywhere between 5 to 8 years to be able to develop new standards ground up, go ahead and get it to a point where you can prototype it and test it and go forth and get a TSO, which is the short form for a technical standard order. And those are orders that are issued by the relevant aviation regulators, so that we can get the TSO, and then we have to go ahead and either type certify that on aircraft, or supplemental type certification needs to be done on the aircraft. And then those equipment are fielded, and then you can start seeing those equipment volumes. So we're talking about anywhere between 7 to 10 years for equipment to be standardized, developed, fielded, and then there's a 25-year time frame over which that utility of the equipment is looking to be amortized by the aviation stakeholders. And we're, in this case, I'm looking at OEMs such as Boeing, Airbus, Bombardier, and looking at my colleague over here, Dave, and other people in the operator industry, such as American, United, and other airlines, when they go ahead and buy this equipment, field it, and use it. So when you look at that kind of a time frame over which things evolve from an aviation perspective, and compare it to some of the other systems that evolve much faster, the question becomes, how are you going to be able to be compatible with these other systems, be it in-band compatibility or near-band or adjacent band compatibility? And that harkens back to what I was talking about earlier, which is to be able to provide clear guidance from an aviation perspective on what spectrum compatibility means, what are the guidelines under which these companies exist, what are the requirements for any other system that may come and operate near band or in band or adjacent band. Then I'll pause, Andy, and if you have any thoughts or questions, I'll take that offline.
Thank you, Simon. We're getting near the end, and I want to have a chance for some Q&A because we've had a couple of questions coming from there. But one's just very quick, because it's a topic at the moment is UAS, and it affects Spectrum very quickly. So if I can just get a couple of quick words from each of the panelists on UAS Spectrum, given there's been a lot of work in RTCA and SC228 on the 5030 to 5091 megahertz, which is part of the old MLS Spectrum. And there's also been questions about whether 5G may do UAS command and control or CMPC links as well. Just a very few words, given we're at the end of time almost, from each of the panelists on their thoughts about using non-aviation spectrum for aviation functions.
Well, Andy, this is Dave. I can go ahead and just start that particular conversation, if you will, briefly, and I'll make it as short as I can. You know, UAS is will have a significant growth path as different players come online, and you start looking at both the military and general aviation. And with that UAS, the criticality is that you know, if it's flying anywhere near a particular airplane, if you will, or close to an airport, you know, you can do some simple math. You know, our approach speeds are 200, 250 miles an hour. And what we don't want to do is have any encroachment from any type of UAV into that particular airspace. The signal loss, and part of that is GPS. We need to really protect the GPS spectrum as it relates to the UAS area. And in fact, UAVs, not only for location and flying, but if the UAV itself loses its GPS signal, it uses that for stability. And then off the UAV goes into different areas. And so we've had a couple of recent events that have highlighted that. Not, by the way, not United, the UAV, the UAS in general, have had a few events of UAVs just flying off. And so it is a critical infrastructure that we think needs to be closely looked at, closely protected from our standpoint. Back to you.
Thanks, Dave. So, Mike, any literally few words, comments on that before we go to the Q&A?
Sure, real quick.
Yeah.
Did we just say me? I'm sorry, Mike.
Mike or Sai. I think we've got about 30 seconds before we need to get to a Q&A to finish up the session.
Okay, I'll let Sai go.
Go ahead, Mike.
Okay, thanks. No, I'll keep it short. Yeah, I agree with the comments by Dave. One of the real challenges is trying to find spectrum that can be protected for the most critical functions like command and control and detect and avoid. We have the interest by other commercial entities that have interest in the same spectrum. So we have to try to deconflict that. One of the biggest challenges is the fact that the UAS industry is moving much more rapidly than the regulatory side. And when you look at the variety and diversity of types of UAS or UA equipment, it's very challenging to have regulations to keep up with it. But I could tell you from the FAA side that there are meetings going on daily to meet that challenge. Thank you.
Thank you, Mike. Okay, well, we've got a few minutes left at the end. Given all the discussion, what I suggest is we move to a very quick Q&A. I'll hand back over to Terry to MC this part.
Hey, thanks, Andy, and to the rest of the committee. We've got a number of questions that have come in, and some of them have already been addressed. But one question I found fairly interesting is that aviation has been sitting on a lot of valuable spectrum, such as MLS, which I think we've been sitting on since 1947. Do we need to be doing something about those bands that we're not using anymore before we start going out and looking for more?
Yeah, Terry, this is Sahir. I'll take the lead of that question, if I may. Depending upon the application that we're trying to support, that's going to strongly drive the utilization of spectrum. If this is an application that can be implemented in that segment of the C-band, the propagation characteristics are appropriate, the effective isotopic radiated power and the receive characteristics are appropriate, definitely we can go and look at what that specific slice of the frequency band has to offer. But if you're looking at a system that has different characteristics, so for example, if you're looking at a system that would be pulsed and it's a system that has a need to have radius over several hundred kilometers, line of sight at altitude, C-band may not be the best option. You may have to start looking at L-band. Again, on the flip side, if you're looking at a system that's going to be SATCOM based, you can definitely start looking in the KU/KA band. And the driver for implementing those systems is primarily SWAP. And then once you figure out your SWAP-C size, weight, and power cost constraints, you're going to be able to figure out where in frequency you can actually field the system and see if it's viable. So essentially, the decision on frequency is not a decision that will be made in the void of the business case or the SWAP-C constraints. They'll have to be made together. I'll pause at that and turn it over to my colleagues here.
Any other thoughts on that?
This is Mike. Can you hear me?
Yeah. Yes.
Okay, sorry. Yeah, I'd like to at least address the MLS band. I think some people already know this, but it may not be known to some folks that are not close to aviation. But the 5,000 to 5150 megahertz portion of the band is actually starting to be used for a new system called Aeromax, which is a WiMAX technology, which is used for an airport land, and that's been used and implemented in at various airports today. Also, we're looking at some implementation of UAS in portions of the 5 gigahertz band. So I just wanted to make sure that people are aware that at least that spectrum, which had been unused for a long time, is being utilized. Thank you.
And we got time for maybe one more question, and there's probably not an easy answer to this, but There seems to be a lot of competition in things like GNSS, GPS, Galileo, GLONASS, and a lot of these things are being pushed by member states, where when we look at things from an OEM perspective or from an airline perspective, we want to have common standards as the best way for interoperability. And that also helps drive reliability and cost. Is there anything the industry can be doing to help convince some of these member states that it's better to look at it that way rather than trying to get competing systems out there?
Perry, this is Sai here. As you mentioned, it is a fairly complicated question to address. So let me start with trying to address that in parts. Every nation state or stakeholder that is fielding these systems have a desire and a goal to be able to elicit benefits from said system sooner rather than later. And for that to be able to happen, you have to be able to have the entire ecosystem available for that system to be utilized. So from an aviation perspective, that has to happen. You have to have manufacturers be able to go ahead and design radios to that system. You have to have operators start fielding those radios. But when you look at a system, for example, such as the Baidu system, if that system needs to be adopted sooner rather than later, as long as that system is amenable to be able to be added as an additional constellation to the existing set of GPS or Galileo and or GLONASS constellations, that would be relatively simpler and easier going forward to be able to harmonize it and have common standards and include that system as part of the common standard baseline from a radio perspective, so that radio manufacturers such as Aerospace and other manufacturers will be able to design radios to be able to accept signals from the Baidu system and utilize it. And this was one of the other reasons why when the harmonization for GNSS systems were done, it was performed from the perspective of ensuring that the frequencies that these systems transmit on for safety of life are lined up, except for GLONASS as it stands today, which may change in the future, 5-15 years. With GPS, Galileo, and Baidu do transmit on the same frequencies for both L1 and L5 bands, which makes it more straightforward for the receive equipment to be able to receive those signals and process and utilize those in parallel in the same radio that would be TSO to a given standard. Over.
Great. I think that's a great answer and a great wind up for the panel. So I'm going to thank Andy and the rest of the panelists for a great discussion. I know there's a number of other questions that have come in. We will capture those and get those to the panelists and get those answers emailed back to those of you that have asked some questions. So thank you. Obviously a lot of passion around this topic, and appreciate all the comments from our panelists. So RTCA serves the aviation industry by providing minimum operating performance standards that serve as a basis for government certification of equipment that's used by tens of thousands of aircraft flying through the world's airspace every day. But at the core of RTCA are the people, the hundreds of dedicated individuals from the US and around the world who come together to develop comprehensive, industry vetted and endorsed recommendations. And each year, RTCA presents some awards to some of our special committee members who have made significant contributions to RTCA standards development and our documents. So I'd like to invite Rebecca Morrison, one of RTCA's program directors, to join us to make a presentation to a set of committee awards for this month. Rebecca?
Thank you, Terry. I was very excited to get to present the awards today because both of the committees receiving awards deal directly with the spectrum issues we just spoke about. The first set of awards is for special committees 236, which is standards for wireless avionics intercommunication systems within the 4200 to 4400 megahertz band. And that band might sound familiar to you because the WTU approved this band for use in wake systems in 2015 if they could show non-interference with radio altimeters, which is what the committee has been working on for a long time. And in 2019, they produced DO 378, the MASPs for coexistence of wireless avionics intercommunication within 4,200 to 4,400 megahertz. And this document defines the performance requirements and a means of compliance for showing non-interference of a wake system with the radar altimeter on ship and non-interference with installations on other aircraft. Being recognized by Special Committee 236 for outstanding leadership in the development of DO 378 is Radek Zakshirsky from Collins Aerospace. Being recognized for their contributions as significant contributors are Thomas Meyerhoff from Airbus and Dr. Dave Redmond from the Aerospace Vehicle Systems Institute. I'd like to congratulate Radek, Thomas, and Dave for their hard work and the whole committee for getting our first MASPs released. They are still working, and if you have interest in this committee, you should contact RTCA. Our second set of awards goes to Special Committee 223, which is the Internet Protocol Suite and Aeromax. And this is the committee that wrote the Aeromax standards that our panelists just told us about. The document was DO 379, Aviation Profiles for Internet Protocol Suite. For outstanding leadership, we would like to recognize Brent Phillips of the Federal Aviation Administration, who has served as the government authorized representative on this committee, I think since it was initially established, and provided leadership in the creation of this document as well as the previous documents. And we would also like to recognize as significant contributors, Madhu Nuraula, I apologize, Madhu, of Collins Aerospace, and as additional significant contributor, Dongzong Sang of the MITRE Corporation. Please join me in congratulating all of our award winners today. Like I said, both committees are still active, and we look forward to more products and from them. Thank you, Terry.
Well, thanks, Rebecca, and congratulations to this month's award winners. And next month's webinar will again recognize another set of our outstanding committee members for all of the great work that they've been doing. Before we move on, I want to give a special shout out to Captain Chuck Stewart, who is stepping down as chairman of our Special Committee 214 as he's retiring from United Airlines after 23 years. Captain Stewart's been a significant contributor to the aviation community, not only as an aviator, but also as a technical expert and an outstanding leader. Chuck served 21 years in the Air Force as a tactical fighter pilot and a test pilot. He had several leadership roles in the Air Force, culminating his last assignment as commander of an A-10 F-16 flight test squadron. After the Air Force, Chuck became an Airbus A320 pilot for United Airlines, and he has held several management pilot positions during his 23 years at United. Besides chairmanship of SC 214, he supported several other RTCA committees, SC 206 and SC 222 to be specific. He's also served as the industry chairman of the Datacom Networks and Infrastructure Working Group and actively participated in numerous Datacom groups. And he was one of the founding fathers of the Electronic Flight Bag Users Forum. In addition to the technical excellence and leadership mentioned, we thank Captain Stewart for the humility that he's shown and the positive influence on others throughout his career. Thank you, Chuck, for all you've done for RTCA and especially the entire aviation industry. And congratulations on your retirement. Again, I want to take a moment to thank our sponsors for today's events. Even during these difficult times, these organizations have been gracious enough to make today's webinar happen. And again, as I mentioned, if you go to the handouts tab on the big marker platform, you can download some additional information about our sponsors. So again, a shout out to Collins Aerospace, NBAA, American Airlines, AOPA, and Garmin as sponsors for today's webinar. Your continued support to the industry and to RTCA is greatly appreciated. To conclude today's webinar, it gives me great pleasure to introduce Mr. Peter Dumont, President and Chief Executive Officer of the Air Traffic Control Association, or ATCA. Pete's career spans more than 30 years in aviation, starting from his beginnings as a U.S. Navy air traffic controller to Chief Operating Officer of the North American sector of a $3 billion defense contracting services company, and now, of course, is President and CEO of ATCA. In his current role, Pete serves a membership of over 3,500 in all segments of the air traffic control and ATM community. Pete represents ATCA on the Next Gen Advisory Committee and the Drone Advisory Committee Working Subcommittee. He also sits on the Policy Board of the U.S. Contract Tower Association, the Unmanned Aircraft Safety Team, and the FAA's ARAC on controller training. He's a recognized expert in the field of aviation and one of our industry's most admired gentlemen. Pete's going to speak with us today about some of the challenges of introducing artificial intelligence and machine learning into the cockpits and control environment. Pete?
Thank you, Terry, and thanks RTCA for having me here today. And welcome to my home here in Tennessee. Welcome to the world of COVID, and welcome to the way we do things now. I'm used to being on a stage and looking at you and interacting with you, but this is the way we do things now, so we'll power through it. My name is Pete Dumont. I'm President and CEO of the Air Traffic Control Association. I'm here to talk to you about machine learning and artificial intelligence today, and how we can use it in aviation, and is aviation ready for it in the control environment and in the control room. As you can see from the parentheses on the slide, it says, spoiler alert, we're not ready. And I don't believe we are ready, which doesn't mean that we can't get there, doesn't mean that AI doesn't have uses, doesn't mean we're not using it in some places already. What it means is we have to ensure that as we introduce AI into the operational environment, we do it with a measured, moderate, and safe approach. Because when we fail in aviation, we fail publicly and we fail catastrophically. So when we talk about AI, what are we actually talking about? So what's the definition? No one really agrees on the definition. The term was coined in 1956 by John McCarthy at Dartmouth University. And since then, AI has had its dips and it's had its peaks in the way it was accepted and the way it was used in society. In 1956, it took a whole room full of computers to do the simplest of calculations and computing jobs. Now, you can basically do those same jobs on your iPhone. So what we've done is, as technology's increased, as we've had chipsets like NVIDIA that have tremendous computing power and are the leaders in AI, we've seen the capabilities of AI being introduced into our lives and into aviation. So, but I want to make one thing clear. When we're talking about AI, we're not talking about automation. So when we talk about things like automation, we're talking about things like autopilot in an aircraft. So an autopilot in an aircraft is programmed with certain parameters to do certain tasks. It takes the model of the aircraft and it figures out how to fly the aircraft based on that model and the performance characteristics of that aircraft. NASA did an experiment called Learn to Fly. And what they did is they took a remote control aircraft and they put it in the air and they had put it into turbulence, and they had the autopilot take over to try to level the aircraft. The aircraft was porpoising. The autopilot couldn't figure it out and couldn't get the aircraft under control. They then let pilots do it remotely. The pilots couldn't get it under control. Once they introduced AI into the system, and they didn't model the AI after the aircraft, what they did is, which is amazing, they took what they wanted the aircraft to do and how the aircraft works. They taught it pitch, roll, and yaw, and they told it level off the aircraft. 3 to 5 seconds, the aircraft was level and flying in turbulence. That's AI learning how to do something based on the input it's taking. It could have prevented maybe things like Air France, where the pilots were getting bad information and then making decisions based on that information. But they were using knowledge based on what the parameters of the aircraft was instead of what they wanted the aircraft to do. So again, a little bit more about what's AI. So AI is the encompassing sphere we're talking about here, which also has machine learning and deep learning in it, as you can see, and you can see the definitions of that. So We use AI in our lives every single day. You can see it from the examples here on the slide, but you can draw from your own experiences. If you have Alexa in your house, or Google in your house, or Siri on your phone, you're using artificial intelligence. Those are the voice recognition tools, and what they do is they talk to the computers, and the computers contain the artificial intelligence, and they make decisions and recommendations based on your input, your queries. Same thing happens with Netflix. So if you keep asking Alexa about different things you want to buy, Alexa is learning about the things that interest you. So when you go to Amazon Prime, or if you ask Alexa, it will make a recommendation of things you might want to buy, with the ultimate goal of knowing what you want to buy before you know you want to buy it, which that's a little scary. And, when we talk about AI, we think about some scary things like 2001: A Space Odyssey, HAL, Skynet, and Terminator. And although those seem kind of far-fetched because they're movies, there are people that are seriously concerned about artificial intelligence taking over for human intelligence and controlling its own environment. But that's a completely different subject, and we could go into that for hours. It's also used in aviation now. You see it in the examples that are on the slide here. You see it in preventive maintenance and maintenance in general of aircraft. So what AI does is it can look at a part, and it's been told by image recognition what the part should look like brand new. And then it compares it to what the part looks like now, and it figures out the part is worn down a certain amount, and it can predict a failure point in time, or it can tell you how worn the part is and what you can expect to do. And that helps you prevent a failure before you do the maintenance, which is very beneficial. So what are our goals here today? What we want to do is we want to talk about how to get AI into the cockpit, how to get it into the control environment, and what are we going to use it for? We're going to use it to increase efficiency, safety, load on the human being, so the human being has less to think about and less to do, concentrate on flying instead of on the things that the computer could do for them. So the challenges of introducing artificial intelligence into the operational environment. One of the main challenges that I see and that I'm concerned about is if you take artificial intelligence and you put it into a control environment, the way artificial intelligence works is it learns. And as it learns, it modifies its code. So you tell artificial intelligence you want it to do this inside the aircraft, and you put it inside the aircraft, and you put it inside multiple aircraft. And based on the parameters that were set for it to learn, it will learn different things. And different AI in different aircraft will learn different things. So when we certify an aircraft or a system to go in an aircraft or a system to go into air traffic control or ATM environment, what we do is we verify it and we validate it. Does it perform the same way every time? Does it perform the task it's supposed to perform? And do we understand how it does it? Because as soon as we put it into the aircraft, we have to ensure and be confident that it's always going to do it the same way. Artificial intelligence doesn't work that way. Artificial intelligence takes input, and we have to determine where we're going to get that input from. Is it going to be input that we get from reliable sources that are good for flying an airplane? Or is it going to be from, for example, the internet on sites that are unreliable, untrue, conjecture, and people that, quite frankly, don't know what they're talking about, and put out papers that artificial intelligence can look at, read, and make decisions on? So that's a exaggeration for point. But the fact that artificial intelligence, once it's in an aircraft, can change its initial programming means how can we validate it and verify it? The minute it changes one iota of code, it's no longer verified and validated. We no longer know what it's going to do. And we've seen this happen in experiments in real life situations. NASA has had experiments where they programmed AI to do a certain task, and it did the task, got better at it, and they wanted to know why. So they examined the code. The code has changed. They didn't know how the code had changed. That's the problem. If we don't understand it well enough to know what it's going to do, then we can't put it in an aircraft that has passengers at this point in time. Now, a lot of people say there's a solution, which is called bounding. So with bounding, you use the artificial intelligence to get to a certain point of efficiency in the testing phase. Then you bound it. You don't let it learn anymore, and you don't let it change. And then you take that and you put it into the aircraft. Well, that's all fine and good, but we haven't put AI in the aircraft, have we? We haven't increased the efficiency of the flight environment. We've just increased the efficiency of how we produce the part that we put in the aircraft. So that's the main challenge that I see here of introducing artificial intelligence into the cockpit or the control environment. Now, in the control environment, controllers could use it and do use it for weather prediction, for example. We could use it for things like recommending the most efficient route, the best time to fly an aircraft, and then working collaboratively with pilots to determine how we do that, when we do that. But the difference there between letting the AI make the decision is the human still makes the decision based on the information it gets from the computer. So do I think we're ready for artificial intelligence in the control environment? I do not. I think we can get there, and I think we have challenges to solve, and I think some of the smartest people around are working on those challenges. NASA has some very interesting programs going on. DARPA has some very interesting programs going on as far as artificial intelligence is concerned, especially with things like you just heard about, spectrum management. Artificial intelligence is now helping with spectrum management in a dynamic environment. When one spectrum isn't being used, automatically switch to that spectrum to use that spectrum for whatever the task is, instead of defined, layered, segregated spectrum layers. So I think AI is very, very interesting, and I wish we had more time to talk about it, but we're just about out of time here. So I'd just like to leave you with one thought, that artificial intelligence has unlimited possibilities. And as we see new business models being developed and new entrants into the airspace, artificial intelligence is going to make a stronger and stronger push to get into the control environment. I think we'll get there. I just don't think we're there yet. So again, I'd like to thank RTCA. I'd like to thank Terry, and thanks for listening. Have a good day.
Well, thanks, Pete. Very informative, very thought-provoking. Appreciate your time. Well, this concludes today's webinar. My sincere appreciation to Andy Roy, Dr. Tsai, Michael Richmond, Captain Dave Sobrano, and Pete Dumont for your valuable contributions today. Also, congratulations to each of our committee award winners. And again, thank you to our sponsors for today's webinar, Collins Aerospace, the National Business Aviation Association, American Airlines, the Aircraft Owners and Pilots Association, and Garmin. And again, remember to go to the handouts tab on this platform to get some more information about our sponsors. For the audience, thank you for joining us today. I hope you found today's presentations educational, inspiring, and evolving. And again, these webinars are being recorded, so if you want to review anything that was presented today, or if you want to see some of our past webinars, you can do so by going to the RTCA YouTube channel. Please join us again next month on September 16th at 1:00 p.m. when we'll feature a panel led by Mr. Max Fenkel of the Aerospace Industries Association on the current state of counter-UAS activities. During the webinar, there's going to be a discussion on some of the standards development RTCA is working on for this new technology and the challenges related to ensuring the safety of the national airspace system. You're going to hear from both industry and government experts on this topic, learn from their expertise, and get their views on the importance of getting this right. So I hope you'll be able to join us. Thank you again for being with us this afternoon, and have a great day.